This is Gail Langevin of the Langley History Program Office. Today is May 21st, 2007, and I'm interviewing Dr. Bruce Holmes. Dr. Holmes, what was your first research project at Langley?
I came to Langley in 1974 as a graduate student from the University of Kansas. I had a project that was called the Advanced Technology Light Twin. It was a twin-engine aircraft with a wing that had been modified to incorporate a high lift and systems and a spoiler roll control system. It was also the first test in flight of a computer-designed airfoil. It was called the General Aviation Whitcomb 1 airfoil, GAW1. So we were all eager to see whether these new computer-designed airfoils could work the way we imagined they would. The project started in 1974 and lasted until about 1976, and I finished my doctorate on that program. And we sent the airplane back to Piper, who owned the aircraft. We'd leased it from them for the project. But at the end of the project, we had the airplane in the full-scale wind tunnel. And one of the fellows, branch head that was in the building 1244, the flight research hangar at the time, suggested that I put a boundary layer mouse on the wing, and so I did, and we measured some boundary layer behavior and saw something very strange. And what we saw that was strange was the laminar flow profile of the boundary layer, when in fact what we fully expected to see, both because it was a wind tunnel and because the airfoil was not designed to be laminar, it was a surprise to see that profile. And so we followed that up, just kind of thinking things through at the time. But then I remembered someone sending me a note with a newsletter piece from Burt Rutan talking about one of his aircraft called the Very Easy, that when it flew through rain, the person who built it, I think, wrote this newsletter article, that when the airplane flew through rain, it was a canard designed, wing in front, wing in back, tail in front, if you will, that the airplane pitched down. And it was like somebody played a movie in my head. I could see sort of what was happening, that the laminar flow on the forward wing was being disrupted and made turbulent, and because the wing was so thick, the flow was separating at the trailing edge of the wing, and as a consequence, the forward wing was, or the tail, if you will, in front, was losing lift, and the airplane just gently pitched down. And so I long story short, rented a Very Easy from a person who had one up in Maryland. We brought it here. We equipped it with some sensors, very primitive sensors at the time. We didn't have flow visualization techniques for laminar flow. But I put a little tube out on the wing, taped it down, and then brought the little pneumatic tube in through the cockpit window and put one of those little foam inserts, stuck the tube through there and put it in my ear. And you can hear laminar flow, according to the books at the time, different from turbulent flow. The laminar flow would go hiss, and the turbulent flow would go shh. And so you could kind of tell which was which if you had a comparison, which we did just by rolling the airplane around and making it go laminar and turbulent. I could hear it go laminar and turbulent. I said, holy cow. So I called Burt Rutan, and I said, Burt, we have one of your airplanes with laminar flow on it. And his reaction was, no, can't be. You know, the airplane's not designed for laminar flow. This was sort of the prevalent view at the time, that laminar flow wouldn't work on airplanes in flight. This is what was in the textbooks. I think maybe one of the reasons I was undaunted by all of that was because I had never taken a boundary layer course, so I hadn't been taught laminar flow didn't work. And so, you know, we talked to Burt a little bit about this, and he explained why he believed it couldn't be true. And he said, but if you really think it is, I'd be glad to loan you a couple of my airplanes out here in Mojave if you want to come out and show me, basically. So Phil Brown and I loaded up an airplane, launched out to Mojave, and we spent about a half a week out there flying some of Burt's airplanes and equipping them. At this time, we had some flow visualization techniques that we'd perfected, really, using sublimating chemicals at the time. And we had methods of tripping the boundary layer to prove with the trip on and the trip off, the difference in the performance of the aircraft. So we did all of that, and I have one of my favorite pictures of Bert is standing in front of the wing of the airplane after we landed and taxied it into the hangar with the sublimated chemicals showing where the laminar flow is, and he's giving one of these, oh, what do you know, salutes, And so we then went on over a period of the next 3 or 4 years, and we tested several different aircraft all the way up to Citation 3, a transonic business jet, very large aircraft, and a Learjet, and demonstrated that the laminar boundary layer was vastly more robust in practical airplane surfaces than any of the previous research would have suggested. And that was a consequence mainly of the fact that we could build smooth wings as contrasted with the wing manufacturing methods of World War II. So that was a couple of the first projects I was involved in over the first 7 or 8 years that I was here.
Those sound like very exciting projects, especially working with Burt Rutan. Did any of that work lead into the Advanced General Aviation Transportation Experiment, commonly called AGAT?
Yes, in an indirect sort of way. I had been working with that industry, the general aviation industry in the U.S. from the very beginnings of my career in NASA, and so I'd kind of grown up with the people who by the time the AGAT Alliance and the whole concept of the AGAT program started to take form. And so these were people that had risen in the companies to senior levels of management and so forth. And so I could go out and tell them at the beginning of our thinking about AGAT that, well, there are some things we could do together if we worked in clever new ways that could advance the cause. At the time, we called it revitalizing the U.S. general aviation industry. But actually, it was more like vitalizing and, in fact, stimulating the development of a new industry. We started AGAT based on some work that I had done in the late 80s. I put together a presentation that was called The Role of Technology in Revitalizing the U.S. General Aviation Industry. And I went around to anybody who would listen and gave this talk all over industry, all over academia, all over government. And then that effort sort of culminated in a workshop in Washington, D.C. in '89 called The Role of Technology in Revitalizing the Industry. And in fact, Burt came to that workshop. We had the FAA there, we had the General Aviation Manufacturers Association there, we had some academia people there. AAA co-hosted the workshop. And so the bottom line was, it's not just technology or a specific technology like more laminar flow or lighter weight structures. You actually had to do everything. You had to do something about propulsion, something about avionics, something about the way airplanes are designed and manufactured, something about the aerodynamics. Everything had to change. It wasn't just one little piece of the story. So we continue to do our homework about what if, and you could sit in 1989 and look forward. You could look forward about 15 years and you could see what was going to happen in navigation technology with satellite navigation and what became GPS. You could see what was going to happen with computers and the revolution in the cost of computing, Moore's Law as they call it. And you could see what was going to happen with radios. They were going to go from analog to digital. You could see what was going to happen with materials, and the properties of composite materials. You could see the possibilities of new engines and new power plants for aircraft of this sort. And so the question that I was carrying around in the back of my head was, so what would it look like to have all of these technologies come together and enable there to be what we in later years termed more widespread use of smaller aircraft in community airports for public transportation. And so the drive, we didn't say it in those words back in 1989 and the early 90s, but that's what we were interested in. So when the nation needs alternatives to the increasing congestion on the highways and the predictable at the time growth of congestion in the hub and spoke system, what alternatives might exist? And so that was an underlying drive behind it all. And so when Dan Golden became the administrator, he went to Oshkosh, eyes wide open, said, my goodness, this innovation here is just spectacular. He met with industry leaders. They had been the same ones I'd been talking to for years about the potential for technology to help revitalize things. And again, long story short, he said, fine, here's some money, you've got 8 years, go make it happen. And so we put together a multi-center program with NASA Langley, NASA Glenn, NASA Ames at the time, and started on the business of designing an alliance. And so that was both one of the challenges of making the whole concept work, and in the end, I think one of the great benefits was using an alliance mental model.
So I think between Agate and the next phase of that program, you went to the White House Office of Science and Technology.
I did.
And what were your duties there?
Well, I was working directly with the senior aviation policy analyst for Neil Lane, who was the president's science advisor at the time. My motivation of trying to find an opportunity like that was quite simple. I could see, at this time it was the late 90s, I could see what was going to happen with the technologies that were coming out of Agate. And they were affecting everything, and they were actually affecting them in ways we didn't quite anticipate, with the creation of actually new companies. So we wound up seeing new companies like Eclipse Aviation, and in the end, even companies like Toyota and Honda taking interest in Atom Aircraft, and Embraer in Brazil, and others taking interest in using these technologies to build a new generation of aircraft, as well as some of the legacy industry companies like Cessna and Raytheon and others. And so I could see the airplane stuff, if you will, coming together in a nice fashion, and yet this idea of public transportation was something I didn't really feel comfortable that I knew enough about to organize my own thinking, much less help organize the thinking of others about what might make sense. So I put together a little road trip, if you will, around what I call the nation's transportation enterprise. And so I figured, well, let's spend some time at the White House, at OSTP. I'll spend some time with the DOT, and then in the end, what that all led to was spending a couple of years in the formation, helping with the formation, leading the strategies development for the Joint Planning and Development Office for transformation of the U.S. air transportation system. So the duties I wound up working at the Office of Science and Technology Policy at the White House were organized around a couple of things, one of which was this idea of a President's Blue Ribbon Commission on the future of the U.S. aerospace industry. And so I supported the development of that commission from the OSTP office, and helped basically with just the organizational logistics and getting that out the door and moved up. One other thing I helped with was trying to think through this structure of the relationships between all of the players in the nation's transportation enterprise. DOT, of course, FAA, of course, NASA, DOD, Department of Energy, Department of Commerce, and of course, after 9/11, Department of Homeland Security, and the White House. And so all of these players have a role, and the roles sort of have to be thought of as part of an architecture among all the players in the enterprise. And so we put together a proposal while I was there at OSTP to have those departments and agencies work together. Well, it got shot down big time, and so it was a bit of a surprise. There was what you could probably oversimplify and say was a bit of a turf issue there at the time, and yet the idea had merit. And so the commission that we've been working on, the President's Commission on the Future of the U.S. Aerospace Industry, came out with some recommendations that something had to be done. And those came about a year later. And so the something turned into a recommendation by the FAA and NASA and DOT to form this Joint Planning and Development Office for the next generation air transportation system. And so I at the time that was starting to take form, I was working up at the DOT National Transportation System Laboratory in Cambridge. It was called Volpe, and really enjoyed working up there, sort of seeing the inner workings of how transportation economic analysis, transportation policy analysis are all conducted in order to support decision-making at the national level.
So most of your time at Volpe was spent on policy analysis?
Yes, and helping translate this idea that I was still working toward, which was, again, more widespread use of smaller aircraft and community airports for public transportation, into, okay, so what has to happen at the federal, state, and local level? And I learned a lot about the relationship between the federal and the state levels that helped me think through and talk about and lead the discussions about what could happen there.
So the JDPO still is in existence today, and what role does that play?
Well, JPDO is the organizing body of these 6 departments and agencies plus the White House, working towards the goal of what do we do in the year 2025 when the hub and spoke system can't take any more traffic and there's about a 300% increase in demand or more. And the airspace has to change. The airplanes have to change. The airports have to change. Everything really has to change. That's why we call it transformation. So the JPDO is still managing the goals, the strategies for transformation, the goals and the technology structure. They've published a concept of operations document which carries along many of these technology visions, if you will, that we've been working on all these years.
So if we could backtrack just a minute back to Agate, and eventually another program was started called the Small Aircraft Transportation System, or SATS.
Right.
And how did that build on Agate and what you learned at the White House and at Volpe?
Yeah. What happened with Agate in the end was basically a definition of industry shared design guidelines, standards for systems and architectures, and certification methods for these new technologies to make it into the aircraft of the future. Standards for things like airbags, crashworthiness design approaches, the means by which you could migrate commercial off-the-shelf computing hardware and software into the cockpits of airplanes to replace what we affectionately called the steam gauges of the 20th century, with basically all glass cockpits, which has now become state-of-the-art. So Agate got the airplane ready, right? And the work at the OSTP and Volpe and JPDO helped prepare, in my mind anyway, helped prepare the architecture, the enterprise, the rest of the enterprise, the rule-making, the policy-making, the big thinking about not just small aircraft and community airports, but the whole picture about the rest of the airport, airspace, airways system and its integration with other ground modes as well. Help prepare our mental models for the idea that this little niche of an idea in smaller aircraft and community airports could play into the big picture. And then the SATS project, Small Aircraft Transportation System project, basically became a focus on how to prepare the airspace for the capabilities these airplanes would bring, in terms, in particular, of having the airplanes self-separate and sequence into airports that don't have control towers, don't have radar, don't have instrument landing systems on the ground, and don't have VHF line-of-sight communications with air traffic control through the traditional means, and yet the airport would have all of the safety and accessibility in near all-weather conditions as though you had all of those things. The reason you didn't need them is because you built them into the airplane, and they were using a satellite system architecture for the communication, navigation, surveillance. So where Agate was about the airplane, SATS was about the airspace and the operation of those kinds of airplanes in the airspace.
So SATS eventually had a demonstration in Danville, Virginia, in I believe 2003?
2005.
2005?
Summer, June of 2005, there was a big demonstration of these operating capabilities with these kinds of aircraft in the National Airspace System. The NASA and the FAA administrators came. The FAA administrator left with a very strong impression that, wow, we can do these things. We can make these technologies work. And I think is, at least indirectly, was a bit of her confidence, a source of a bit of her confidence in what the JPDO was trying to do with that system concept of operations that has been developed now for the way that we could use airports other than the hub and spoke airports in the nation's transportation system.
Do you see the transportation system heading in that direction anytime soon, or do you think it'll be more of a long-range plan?
Well, I think it'll take time to unfold. The first steps are happening now. I came home last week from a trip using one of the first companies to develop an on-demand air taxi system concept. And I was out in the Midwest and flew home, bettered the time required on the airline system by quite a bit at a competitive cost. And so it's already sort of in an early adopter phase. But I like to point out that the growth of this new industry, the on-demand air taxi, jet taxi fleet industry, will be relatively slow. I mean, it'll show up in a little bit here, a little bit there. There are several companies that plan to start operations, some this year and some next year. And their pacing item is how quickly can the manufacturers of these new aircraft deliver the aircraft for these fleet operations. So it's already begun. It'll start off slowly. It'll pick up speed as the aircraft manufacturers are able to spit out airplanes faster.
So what do you think are the most were the most challenging issues of agate and SATS?
Well, we didn't know it at the time. If we had, we might have questioned our sanity about trying out the whole idea of a public-private alliance in the case of both of those programs. I mean, one of the underappreciated parts of the Agate Alliance was that the project was that we actually had two goals that we carried forward together. One goal was the technology goal, and the other was the partnership goal. And the idea behind the partnership goal was to make a successful public-private collaboration work. And one of the miracles that happened at the beginning of that enabled, I think, most of the progress that we did make where it worked was getting out from under the federal acquisition regulations and being authorized to use other transaction authorities to develop a negotiated agreement between the members, the parties in the partnership. Allowed us to tailor the intellectual property rights, share in the development of the objectives from the very beginning, instead of having NASA figure out what all the objectives should be and then just put them out on the table. We actually developed them on the table together with the partners. Very different approach than in the past, more like the NACA model actually in some respects. And so the reason that was so challenging was, first of all, we were an odd duck. I mean, there was nothing like this anywhere in NASA or anywhere in the center that we could go to and say, well, how did you do it? What did you do? I mean, we were just inventing every day. It was a new problem. I'd be on the phone with the lawyers every day saying, can I do this? And the answer usually was yes, if you follow these practices. Although the federal acquisition regulations weren't the rules, we had to behave like there was good reasons why those rules exist, right? So making that work was a huge challenge. And then there was a bit of what I would call a cultural challenge of making it work in the center. The traditional way of success of programs at a center like ours, at any research center in NASA, is, okay, well, you win this program and you bring the money to the center and you spend the money here. We didn't do that. We actually won the program, got the money, and then had the money out in the industry, the hands of the partners. And they matched our money, and so we leveraged by more than a factor of 2, actually, through some other leveraging with the Small Business Innovation Research Program. Another great innovation in alliance development, alliance strategies. So we leveraged the resources and we made the decisions together, and so we didn't have control in the hands of the researchers here at the center. And so that was culturally difficult for the center to deal with, very, very hard. And I think in the end, we sort of made it work and accommodated the tensions. And it's interesting to look back on all of that and realize how messy things can feel at the time, but how spectacular the success can be in the end.
So it sounds like one of the significant accomplishments for these two programs was a culture change, but can you elaborate maybe on some of the technology accomplishments that were significant?
Sure. I think in Agate, one of the, two of the, well, maybe three, a few of the big home runs included the ability of the industry to move electronic displays in to replace the analog mechanical devices of the 20th century. And what we did was we worked with the FAA. We sat down at the table, and the FAA said, holy cow, you mean if you replace those steam gauges with these computer systems, the reliability goes up for less cost than the old systems? And the answer is yes. Well, they said, prove it. So we did some proofs. And they wrote, the FAA and industry and NASA together wrote a set of advisory circulars that allowed the FAA then to approve the use of these commercial off-the-shelf computing systems and device drivers and operating systems and so forth in the cockpits of these airplanes, following their rules. And so that was a big breakthrough. I mean, it had an interesting effect in accelerating what probably would have happened anyway, sooner or later. Mm-hmm. And that's very characteristic of all alliances. I mean, the purpose of these alliances is to accelerate something that everybody wants and create the acceleration in such a way that everybody gets something good. The government out of this gets a public good outcome in terms of accelerated development of a transportation capability for the nation. The industry partners get something out of it in terms of accelerated product and services to market. So that's what came out of that. The second one I'll point to was the development of a streamlined materials qualification process for composite systems. And the way it worked in the past for OEMs, original equipment manufacturers, also known as airframers, to develop a new airframe built out of composites was they had to do this very large testing matrix called B-basis allowables. And it would take, one material system would cost $1 million, let's say, and would take a couple of years of testing of, hot and wet and cold and dry and tension and compression and bending and all of these tests to prove to the FAA that the material is okay to use in this airplane. Well, we were in a meeting, several meetings actually over time with the FAA and the industry folks and the NASA folks. And a bit of an aha emerged, which was that the FAA said, well, you've got 5 companies out here giving us all the same data. I mean, you don't know that. The companies didn't know it was the same data, but the FAA did because they got to see it from all these 5 companies. They said, why don't we figure out how to have the material vendor pre-qualify the material and put the properties in Mill Handbook 17, which is the guideline for materials, in this case composites, and have that authorized by the FAA as the means of compliance with the certification rules. And everybody said, well, that's a really radical idea. But in the end, now we've got a Mill Handbook 17 entry for several material systems that now allow the companies, the OEMs, the manufacturers of the airframes, to basically go, say, with a very reduced testing matrix, say to the FAA, this is what we're doing per the guidance. Boeing credits the development of that design, that streamlined qualification process with their decision to use composites in the new Boeing 787 Dreamliner. There are manufacturers of general aviation aircraft that credit the use of that approach to materials qualification with saving them 2 years and $20 to $30 million in developing a new airplane. So these are very significant advances. Plus, we had a lot of standards sort of sharing, if you will, in things like lightning protection, crashworthiness design. There are now airbags in airplanes. This airplane I mentioned, I flew home earlier last week, mentioned earlier, had airbags in it. So these are technologies that are now with us, are now real.
After your work in agates and SATs, you went on to work in Advanced Planning and Programs Office. Mm-hmm. What do you feel were your significant accomplishments there?
The last 3 years were extremely satisfying to me. The center, any organization, not just our center, but any organization faces a significant challenge in being able to think and act strategically. Think and act with a thought in mind that you're going to have to be able to align yourselves with your external environment, in our case, the NASA strategic plan, you're going to have an awareness of all the forces at work in that alignment process, not just the ones in NASA, but the ones in industry, the ones in the world, in energy and communication and transportation and education, in all aspects. So you have to have this ability to align. You have to have an awareness of the forces that make it hard or easy to align. And then you have to have an agility that allows the organization to close its decision loops faster and faster and faster over time in order to maintain relevance to, in this case, the American public. And so the better part of my job was putting together the thought processes by which our center, and in dialogue with other centers, we shared a lot of this thinking as well, could do that, create this alignment through this awareness and have it result in some agility. And I felt very strongly by the time I retired in May of 2007 that the center leadership team had a very strong ability in these directions. Not perfect, but no organization is ever perfect at that, but leaps ahead of where we had started. That's one thing I really felt strongly about. Second thing I felt strongly about was that was really good was this whole idea of taking the insights of these years and years of working in alliance structures and architectures and translating that into something that was fairly easy to use. And so we had a couple of projects in the last year I was working that were ready, ripe, if you will, for alliance strategy applications. And so I helped bring together the dialogue at the center between legal and intellectual property and the center leadership, office of director, the technology side, the finance side, and so forth, and bring those parts together and have a dialogue about, okay, well, if this project is going to make it, the technology in this project is going to make it into the light of day, out in the real world, into applications, what might an alliance look like? And so we developed a little bit of an alliance design tool that now is resident here, and there's some staff assigned and also staff available through consulting arrangements to come in and actually help the center take that design tool and apply it where needed in the 21st century to the way we do business here. And so I was very pleased to be able to take all of this learning and condense it down into something that I could leave behind and have it be very useful. There's a third thing. I'm from a person who had one up in Maryland. We brought it here. We equipped it with some sensors, very primitive sensors at the time. We didn't have flow visualization techniques for laminar flow. But I put a little tube out on the wing, taped it down, and then brought the little pneumatic tube in through the cockpit window and put one of those little foam inserts, stuck the tube through there and put it in my ear. And you can hear laminar flow, according to the books at the time, different from turbulent flow. The laminar flow would go hiss, and the turbulent flow would go shh. And so you could kind of tell which was which if you had a comparison, which we did just by rolling the airplane around and making it go laminar and turbulent. I could hear it go laminar and turbulent. I said, holy cow. So I called Bert Rutan, and I said, Bert, we have one of your airplanes with laminar flow on it. And his reaction was, no, 76. And I finished my doctorate on that program. And we sent the airplane back to Piper, who owned the aircraft. We'd leased it from them for the project. But at the end of the project, we had the airplane in the full-scale wind tunnel. And one of the fellows, branch head, that was in the building 1244, the flight research hangar at the time, suggested that I put a boundary layer mouse on the wing, and so I did, and we measured some boundary layer behavior and saw something very strange. And what we saw that was strange was the laminar flow profile of the boundary layer, when in fact what we fully expected to see, both because it was a wind tunnel and because the airfoil was not designed to be laminar, it was a surprise to see that profile. And so we followed that up, just kind of thinking things through at the time. Can't be, the airplane's not designed for laminar flow. this was sort of the prevalent view at the time, that laminar flow wouldn't work on airplanes in flight. This is what was in the textbooks. I think maybe one of the reasons I was undaunted by all of that was because I had never taken a boundary layer course, so I hadn't been taught laminar flow didn't work. And so, you know, we talked to Bert a little bit about this, and he explained why he believed it couldn't be true. And he said, but if you really think it is, I'd be glad to loan you a couple of my airplanes out here in Mojave if you want to come out and show me, basically. So Phil Brown and I loaded up an airplane, launched out to Mojave, and we spent about a half a week out there flying some of Bert's airplanes and equipping them. At this time, we had some flow visualization techniques that we'd perfected, really, using sublimating chemicals at the time. But then I remembered someone sending me a note with a newsletter piece from Burt Rutan talking about one of his aircraft called the Very Easy, that when it flew through rain, the person who built it, I think, wrote this newsletter article, that when the airplane flew through rain, it was a canard design, wing in front, wing in back, tail in front, if you will, that the airplane pitched down. And it was like somebody played a movie in my head. I could see sort of what was happening, that the laminar flow on the forward wing was being disrupted and made turbulent, and because the wing was so thick, the flow was separating at the trailing edge of the wing, and as a consequence, the forward wing was, or the tail, if you will, in front, was losing lift, and the airplane just gently pitched down. And so I long story short, rented a Very Easy.
This is Gail Langevin of the Langley History Program Office. Today is May 21st, 2007, and I'm interviewing Dr. Bruce Holmes. Dr. Holmes, what was your first research project at Langley?
I came to Langley in 1974 as a graduate student from the University of Kansas. I had a project that was called the Advanced Technology Light Twin. It was a twin-engine aircraft with a wing that had been modified to incorporate a high lift and systems and a spoiler roll control system. It was also the first test in flight of a computer-designed airfoil. It was called the General Aviation Whitcomb-1 airfoil, GAW-1. So we were all eager to see whether these new computer-designed airfoils could work the way we imagined they would. The project started in 1974 and lasted until about 1970.